Okay, so moving on here into our next steps. So we've dealt with those solution mixtures and some of the other processes and problem solving. We want to keep going. Unit 2 is about building the tools necessary outside of the arithmetic. Unit 1 was just the arithmetic. Unit 2 is building the tools necessary to make the dosage calculations involved in Unit 3. And so we had those tools for solution mixing and percents and concentration and stuff. Today we're going to look at another very important tool. I think one of the most powerful tools in math, and that is ratio and proportion. So let's start talking about ratios. A ratio is nothing more than a comparison between two numbers. Or I should say two or more numbers, but for the most part, we're going to be looking at just two numbers. So for example, I have two high school classes running right now. I might want to do a ratio of students in my Math for Health class. Well, I'm compared to my students in my Construction Academy class. Well, I have 6 students enrolled in the Math for Health, and I have 8 students enrolled in the Construction Academy. Now I can write that ratio like that in that fractional form, 6/8. I prefer it like that because there are a lot of things that we want to do with a ratio that are similar to what we do with other items in that fractional form. Another common way to express it is like this, 6 with a colon and then the 8. Or even with the words 6:8, like that. Now one of the things, and we should be careful here, I'll come back to this, but that word 2, we want to be careful that we make sure we use that in the right context. So we said there were some things we are used to doing with fractions that we like to do with our ratios. And one of them is reducing. We're used to reducing fractions, like here 6/8. Both of those can be divided by 2, so we would divide by 2. 6 divided by 2 is 3, 8 divided by 2 is 4. We get that reduced ratio of 3:4. Now again, we were used to doing that with fractions, but we can still do it with our other forms of a ratio. In this form here, 6 divides by 2 and 8 both divide by 2. 6 divided by 2 is 3, 8 divided by 2 is 4, and so it still reduces to a 3:4 ratio. It's just we're not used to this process. We've done this one here with other fractions, so we're used to seeing that process. Now I mentioned this form over here with the word 2 in it. The word 2 implies that these two are separate groups. Separate, whether it's people, groups of people, separate formulas, ingredients in the formula, whatever. Another way I could have worded that was I could have said that it was 6 out of the 14 students, high school students that I currently have, are in the Math for Health. When we use this wording, the out of, that implies that this is part of this total here. So 6 out of 14 is implying that 6 is part of the 14. In medical applications, we have something called a dilution. So we might have a 1 in 6 dilution. So a 1 in 6 dilution is a 1:6 ratio. But the 1 represents a medication or an active ingredient. The term we're going to end up using for that in this class is serum. This might not necessarily be a medication, but it's an active ingredient of some sort. And the 6 represents total solution. So that is not only, that includes the medication, the serum, and some sort of a solvent. And usually it is some sort of sterile water. And remember we said NS stands for neutral solution or normal saline, or basically sterile water of some sort that is mixed with it. So that one part of medication that's on the first number is included also as part of that second number. So because of this, we can create other ratios from that ratio. This is the ratio of serum to total, the 1 to 6. If we wanted the ratio of serum to sterile water, or NS, it would be 1 to 5. Because 6 minus 1, 6 total units minus 1 unit of serum gives us 5 units of sterile water that is dissolved in. And then a little bit less common, but still often useful, is the ratio of saline, NS, to total. So we have 5 units of saline out of those 6 units total. So this works because it's only 2 ingredients. It's called a binary mixture. Not a word you need to know, but binary just means 2. So whenever we have a binary mixture, creates a binary ratio like that, we can create several ratios out of that original ratio where it's 1 in a total, or 2 in 7 would be 2 out of a total of 7, or whatever. We're going to deal a lot more with dilutions at the very beginning of Unit 3 coming up in a couple weeks. Well, let's look at another ratio. It looks like your classrooms all pretty much have similar tables in them from what I've seen in videos. I know some of you aren't in your classroom right now, but I'll leave the tables that are in my classroom right here. And I want to do a length to width ratio. Well, these are 6-foot tables, so they're 72 inches long and 18 inches wide. So the length is 72 inches to a width of 18 inches. One of the first things we'll notice here is that the inches cancel out. We can reduce them out of the fraction. And then as we reduce the fraction, 72 and 18 are both even. We could divide by 2. But if we look closer, we find that both of them actually will divide by 18. So 72 divided by 18 is 4. 18 divided by 18 is 1. Now there's a few points to make here. First, if this were really just a fraction, we'd reduce that to just 4. But it's not a fraction. It's a ratio in fraction form. Kind of like we said with our percents. Those weren't really fractions. It's a fractional form of a percent. It's a ratio. So because this is a ratio and not a fraction, we can't reduce it to just a 4. The ratio has to be a comparison of 2 or more numbers. So we have to keep the 2 numbers as 4 to 1. Second point to make here is this is a special type of ratio. Because that bottom number is a 1, it's called a unit ratio. Because it is comparing something to 1 unit. Certain items are always reduced. We force them to reduce to a unit ratio. This is obviously one that just naturally reduced to a unit ratio. But we'll look at some examples of items that we force to reduce to that. The third point I want to make off of this, and the final point, is we notice that the units canceled out. The inches and inches canceled out, leaving us a ratio with no units. Because the ratio is always unitless, it means it doesn't matter what units we actually use to measure. Here we had inches for the length and width, but it doesn't matter. The 4-to-1 length to width ratio could be saying that for every 4 inches of length, there's 1 inch of width. Could be saying that for every 4 feet of length, there's 1 foot of width. Or it could be saying for every 4 centimeters of length, there's 1 centimeter of width. The units don't matter because they've canceled out in our ratio. So down there we were comparing inches to inches. Up here we were comparing students to students. That is a requirement of a ratio. A ratio must compare numbers with the same label or the same name. So what if we have something like 2 feet over 18 inches? That's feet and inches. They do not have the same name. So right now, that is actually not a ratio. But we can convert 2 feet into 24 inches. And of course, the 18 inches can just stay. Now we're comparing inches to inches, which is just fine. The inches cancel out. We can divide both of those by 6. 24 divided by 6 gives us 4. And 18 divided by 6 gives us 3. This brings us up to the second major difference we have between ratios and fractions. If this were a fraction, we'd split it into a mixed number, 1 1/3. But it's not a fraction. It's a ratio in fractional form. And a ratio, remember, is a comparison between two numbers. We have to leave it as those two numbers. It would not be appropriate to try to split this into a mixed number. So that's a second big difference between ratios and fractions. So I've expressed that the ratios have to compare two numbers with the same label. Well, what if we want to compare two numbers that have different labels? Let's say we go on a road trip and we're going to drive 365 miles and it takes 7 hours. There is no way here that I can turn miles into hours or hours into miles. These are going to have different units, different names. Well, this is what is referred to as a rate. And that is the first big difference between a rate and a ratio. The ratio had to compare things with the same name. A rate can compare things with different names. The second big difference is that rates are often, or almost always, I should say, expressed as what we call unit rates. A unit rate means that second number, just like in our unit ratio, the second number is 1, but we still have the units there, just the number becomes 1. So to do that, in this example, we would take the number in that second value, which is the 7, and we're going to divide both measurements or both values by 7. So the bottom part's simple. 7 hours divided by 7 is just 1 hour. On top, we have to do 365 miles divided by 7. Should have picked an easier number there. 365 divided by 7, what is that? 52.142857143 approximately miles. Now, we wouldn't take it out to 9 decimal places like that. We would round it off. Probably something like 52.1. And we tend to not leave it in this fractional form. We tend to hide the fraction portion in the units. Probably write it like this, miles/hours for miles per hour. So that the fraction gets hidden here in the units. In fact, sometimes we hide that fractional form even deeper with something like this. Let's say that on this trip, we get 24 mpg. Well, mpg stands for miles per gallon. So when we see 24 mpg, we need to think 24 miles per 1 gallon. because that is the form we need it in so that we can calculate with it later when we start looking at proportions. Well, let's look at some examples of rates and ratios. We saw a couple rates there. We're pretty familiar with miles per hour for speed, miles per gallon. We might have, let's say you're at work, you earn $176 in an 8-hour shift. So our rate there is $176 over 8 hours. Now we want to make it a unit rate. Remember, most rates, almost all rates are expressed as unit rates. So that second number has to be reduced to a 1. So we're going to divide by that number. We're going to divide by 8. 8 hours divided by 8 is 1 hour. $176 divided by 8 is $22. And of course, we would write that again with get rid of that fractional form. Write it as $22 per hour, like that. Or we might have a platform that is holding 496 pounds spread out over 8 square feet of area. And look at what this pressure is, what this load is. Well, we have the 496 pounds will be over 8 square feet. Well, again, I don't know why I keep choosing 8 for the second number, but again, the second number needs to be reduced to a 1, so we're going to divide by the numerical part, the 8. 8 square feet divided by 8 is 1 square foot. And on top, 496 square feet, or 496 pounds divided by 8, what is that? 62 pounds. So 62 pounds over 1 square foot, or again, most likely written as 62 pounds per square foot, like that. Other rates you would run into is, looking at consumption rates, ounces per hour. We're going to have all sorts of medical field. We're going to have flow rates. We're going to have flow rates, which will be like 40 milligrams per hour, or 5 milliliters per minute. Drops per minute is one we'll explore when we do our medical or dosage calculations. Rates are going to be one of the biggest calculations we have in our medical math, because most medicines are not administered as single doses, or what we call boluses. They are administered over time. So IV flow rates or administered doses are going to be a big deal. And even for the single dose medications, the rate of concentration, how many milligrams per milliliter, how many milligrams per capsule, those rates determine how much we administer to a patient. Let's look at ratios. Ratios, again, are all around us. There's all sorts of applications. Now, because you're a high school class, I'm going to digress a little bit from the medical side and get into some more general applications first. One of them would look like this. Now, this is the part of the class where we expand your imagination, because I'm going to try to draw pictures. And there's a reason I'm a math teacher and not an art teacher. My drawing is horrible. Anytime I draw pictures, there's going to be imagination involved. Hopefully it's not too much of a stretch. Those might look like two suns or two cells or virus cells fighting each other. What it is, it's actually gears. I'm talking about a gear ratio. Gear ratios, pulley ratios, they all involve the same thing. We're comparing the size between the two gears or pulleys. For pulleys, we'd have to measure the diameter. That's why I use gears, because gears, for two gears to mesh, the teeth have to be exactly the same distance apart. So we can measure the size of a gear simply by counting the teeth. So the gear ratio is the number of teeth in the driven gear divided by or compared to the number of teeth in the driving gear. So those two words, driven and driving, are the key words here. Let's count the teeth to find the size. I'll make a mark here to give us a starting point. We count around there. 1, 2, 3, 4, 5, 6. 16. There's 16 teeth in the big gear. Again, I'll make a starting mark. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 teeth in the little gear. So we have the number of teeth. How do we determine which one's driven and which one's driving? Well, we need some more information. So, back to my questionable artwork. Pretend that looks like a shaft. That bigger gear's on a shaft connected to. Pretend that little can looks like an electric motor. So, the motor is turning the big gear, which is turning the little gear. If I separate the gears, which one stops moving? Yeah, the 10-tooth gear. That is being driven by the other gear. The one that stops is the driven gear. So that 10 goes on top. The other gear is driving the little gear. It is connected to the power source. It's going to turn whether the gears mesh or not. That's the driving gear, the 16-tooth. And of course, we can reduce those. Both divide by 2. 10 divided by 2 is 5. 16 divided by 2 is 8. We have a 5 to 8 gear ratio. So that gear ratio describes a lot of things. It describes the ratio of the number of teeth, but it also, as we mentioned, describes the size of the gears. It's also the ratio of the RPM between the gears. It's the ratio of torque transfers, and several other characteristics about that interaction of those gears is described by that ratio. Another common set of ratios that homeowners run into are these: pitch and slope. A lot of people, even contractors, use these terms as interchangeable. They're not the same thing. So if we're looking at a roof here, we have a span of the roof, and we have a height. The pitch of a roof is that height compared to the span. So let's say that height is 8 feet high and our span is 24 feet. So the pitch is 8 feet over 24 feet. Now again, the feet cancel out because the units are the same. So that's 8 over 24, and both divide by 8, giving us 1 to 3. That is a 1 to 3 pitch, or a 1/3 pitch, it's often called. The slope is slightly different. The slope is a rise, just like with graphing equations, over a run. Well, the rise is the same as the height. The run, however, is the length of one of the sloped surfaces, because the slope is actually describing this sloped surface. The other side is a separate slope it's going down instead of up. So this is the run of that sloped surface, the horizontal component. So the rise would still be the same as the height, the 8 feet. The run would be half the span, or 12 feet. Now the feet do cancel out, so that would give us the 8 over 12. And we could reduce those numbers, but we don't. Usually the slope is expressed as out of 12. It's not necessarily 12 feet, it's actually out of 12 inches. It's the rise per foot. So as I said, this 8/12 describes the angle of that sloped surface. The 1/3 is the ratio of height to span. And what it's doing is on older conventional frame roofs where you had a ridge beam and rafters, that described how high the ridge beam had to be set above the walls, 1/3 of the span. Let's go back to one more mechanical application. Let's look at, we'll have fun with my drawings again. If you're mechanically inclined and have a good imagination, you might recognize those as pistons. We're going to talk about compression ratio. So compression ratio is the expanded volume. So expanded volume is the largest volume above the cylinder. So it's when the piston's at the bottom of the stroke, or what we call bottom dead center. This is the expanded volume over the compressed volume. And the compressed volume is when the volume above the cylinder is the smallest, or when the piston's at the top of the stroke, what they refer to as top dead center. That would be this volume here. So let's say that this is 60 cubic centimeters, and this is 480 cubic centimeters. So the expanded is the 480. Compressed is the 60. Now, of course, the cubic centimeters do cancel out, and both 480 and 60 divide by 60. You could divide by 10, and then by 2, and then by 3. We're just going to divide by the 60 here. 480 divided by 60 is 8. 60 divided by 60 is 1. Now, this is one ratio that is almost always expressed as a unit ratio. So this one just naturally reduced down to have 1 as that second number. But this is one that we would force to reduce down. Even if we ended up with a decimal in that top number, we would force it to reduce to a unit ratio like that. Let's talk about one that almost all of us are going to encounter at some point in our life. That's a debt to income ratio. So we hear a lot of talk about credit scores. Oh, you got to have a good credit score or life's going to get real expensive. Yeah, credit score is important, but a credit score actually is not what determines whether you get a loan. As long as you don't have a horrible credit score, and by horrible I mean like in the 500s, most banks, if you're 600, 625 or above, you can get a loan. But if you have a low 600s, you're going to be paying a higher percentage interest than if you have a good score like in the mid 700s. For example, a friend of mine who's a loan manager, 2 years ago, you could buy a car if you had a score in the mid 700s, a 750, for example, you were paying 1.99% interest. If you had a score in the mid 600s, you were paying 4.9% interest. Now those rates have gone up considerably from there, so the credit score determines your rate. Even with a very good credit score, you can be right around 800. If you have a bad debt to income ratio, you're not going to get the loan because the debt to income ratio actually describes whether you can afford the payment. So let's start with the income, and this is actually one of those inverse unit ratios that we mentioned. So we'll look at what that means in a little bit. So let's start with your income. Let's just say that you make $21 an hour times 40 hours a week times 4 weeks in a month. So what does that come out to be? Like 33.50, something like that, 33.60. 21 times 40 times 4, yeah, 33.60. So it's $3,360 a month in income. Well, then debt Let's say you have a car loan, and we'll just put that at $400 a month. I know now most car loans are way higher than that if you buy a new car, but let's stay fairly conservative here. Let's say maybe you have a student loan. Let's put that at $200 a month. And let's do credit cards. Now for credit cards, I know many of you in high school probably don't have credit cards yet or are using parents' credit cards. They don't let you get away, the banks don't let you get away with just the minimum balance. They have a formula for what is your average balance over the last few months, and then they calculate what your payment should be. So let's say that comes out to be $400. And other expenses like utilities, gas, electricity, rent, if you're renting an apartment, those don't count. Those are not debts. Those are expenses. So they're slightly different. It's only payments on other loans or debts that are counted here. So we add those up, that's $1,000 a month in debt payments. So again, it's income compared to debt. So over here, we'll put our debt of $1,000 a month over our income of $3,360. And we had said this is an inverse unit ratio, which means we divide by the top number. So dividing by 1,000 on top gives us 1, which is what we want. We want it to be 1 to something. Dividing by 1,000 on bottom gives us 3.36. We want this number, this bottom number, to be at least a 3. Usually they say a 3.2. But as long as it's at least a 3, that's saying you're in good standing. So this person has a pretty decent debt-to-income ratio. Many of you are probably barely old enough to remember the big mortgage crisis in 2006, 2007. What happened there was banks were being pushed to make more low-income loans. They were pushing that debt-to-income ratio so that bottom number was down to like 2.5. And so the people could afford to pay, they could afford to make their payments on their mortgage if everything went well for the month. But if their car broke down and they had that extra expense, they couldn't afford it. Or if they got sick and missed a day or two of work, their paycheck was smaller, they couldn't afford it. So it put people in that section where if anything went wrong, they couldn't afford to make their monthly payments. So that's what the debt-to-income ratio does. It describes, can you afford the debt you have? So then the next step is to look at proportions. So let's say we have a ratio where we need, well, the bottle tells us that we have a medication that is mixed with 5 milligrams of medication in every 2 milliliters of solution. And we have a doctor that has asked us for, so let's write this out. This gives us a rate of 5 milligrams in 2 milliliters. And the doctor has asked us to administer to a patient 20 milligrams of medication. So we can line this up to figure out what this, just like we did with percents last unit, to figure out how much to administer to the patient. Well, in our proportion, if we're dealing with rates, the units must line up. This number has to connect with this number. So that's milligrams, this has to be milligrams. And this number has to line up with this number. That's milliliters, this has to be milliliters. All of a sudden, the doctor wanted 20 milligrams, so that goes on top, the milligrams. And then just like what we did last unit to find that missing number in our proportion, we take the two numbers that are diagonal, we multiply them. 2 milliliters times 20 milligrams, that's 2 times 20 is 40. Milligrams times milliliters is milligram milliliters. And then the number that's diagonal to our missing number, we divide by. So we divide by 5 milligrams. 40 divided by 5 is 8. The milligrams divide out, and we are left with just milliliters. Now, for the most part, we're going to skip using the units in our cross multiply and divide, but I wanted you to see that it does work out if you use the units in that calculation. So let's say we need a gear ratio of 3 to 5. And we find a motor that has a gear with 35 teeth on it. We need to know what size gear that we have to have on the other side of that. So we need a 3 to 5 gear ratio. Now this is ratios, not rates. With the rates, we had units that had to match up. We had to have milligrams to milligrams and milliliters to milliliters. Ratios don't have any units in them. So what do we line up? Well, we line up things that describe the same thing. Remember, in our gear ratio, this top number was the, was the driven gear, the one that was being driven by the other one. The bottom number is the driving gear. So whatever goes over here has to be the driven gear matching up with the top. What goes here has to be the driving gear matching up with the bottom. Well, the gear on the motor would be the driving gear. So that's 35 teeth is going to go on bottom. And then we'll go ahead and cross multiply and divide to find the missing number. 3 times 35 is 105. Divided by 5 is 21. So there has to be 21 teeth on that other gear to preserve that gear ratio. Okay, so we are a few minutes early here, but since there's only 2 of you out of the 6 in class, we'll stop there. We will review this a little bit more on Friday before we go into the next topic. Friday is actually kind of a review day anyway. We're going back into percents and expanding on our view of percents. So for right now, if you take a look in the book, page 73, 1 through 39, the odds, dealing with problems with rates and ratios and proportions. So I thank you guys all for logging in today with the bad weather. Hopefully you guys stay safe, and we'll see you all on Friday.